So we looked at why nanomaterials are important. We also looked at supercapacitors, basic concepts of supercapacitors, and also why do we need nanomaterials for assembling supercapacitors. So there are two main important parameters that we came across. One is surface area. So nanomaterials need to possess very high surface area for them to be applicable for energy storage devices such as supercapacitors, as well as there is another parameter, electrical conductivity, which I will be talking more in detail in the subsequent slides when I give my talk. So here is the common assembly of a supercapacitor device. You have two electrodes, and the electrodes have very high surface area, so you can see by the pores structures, and there is a membrane in between. This membrane is an insulating membrane which keeps the charge carriers separated across the two electrodes. So you have accumulation of charges on the two plates, and this stores the charges on the two plates, which gives you energy output. So if we look at the two electrodes, you can see that the electrodes each electrode, the accumulation of charges act like a capacitor. So which is already explained by Professor Fisher in previous talk, that each electrode has capacitor. So if we combine the two electrodes, we have double layer capacitor, and these are two capacitors connected in series. And also it is important to note that there is additional resistance which comes into picture when you have individual electrode. So the resistance comes from the electrodes as well as the separator in between. So you can see that there is an equivalent circuit diagram that can be drawn for a simple supercapacitor, and there is capacitor C1 on the electrode 1 and capacitance C2 on the electrode 2. Now these two capacitance C1 and C2 needs to be equal for a perfect or an ideal supercapacitor. Also, one needs to look at these resistances of the individual electrodes, and one need to minimize these resistance for an ideal supercapacitor behavior. So also we need to look at the components of a supercapacitor when we want to assemble it. So the important components are current collector, electrode material itself, and then the separator and the electrolyte. So these all form the important or the essential components of the device. Now we need to look at the synergy between the current collector and the electrode material for its fabrication. Okay, so I will go through individual components. First I will be discussing current collector and electrode material together. We have looked at synthesis of these materials and individual different methods which can be adopted to make these materials, but when we want to assemble a device, we need to know how to lay these materials together. Then the electrolyte and the separator are different material to fabricate the individual device. So if you look at this here, these are two different pictures or the natural system which you come across. One is fallen leaves, and other side you see grass. One is like a deposition, so you have to have an analogy in mind when I am discussing this. So if you look at fallen leaves, it is like a 2D system. You have leaves fallen in one plane, okay? And then if you look at the grass, it is a 3D system, it's a growth process, right? So among these two, which has high surface area? Grass. But how the two processes are different? It is, if you have to think of fallen grass, it is so easy to visualize it that the leaves fall and it can be done, like you can spread out any material and form a film. So I am talking of an analogy with fallen leaves to a film formation where you have individual material, the leaf is an individual component, and you are trying to make a 2D film. But when you think of a 3D system, now the grass is a growth process. So you cannot have grass grown in one day, right? or you cannot do it like a simple deposition. You don't have individual material that you can make it stand vertically like this. So it's a more challenging process to have a 3D material, right? But why 3D material is important? Because we have high surface area, and for the devices like supercapacitor, we can have very fast ion transport across the electrode as compared to a 2D system. Here is an example, like you are seeing graphene layers, and when the ions have to move in between the graphene layers in a 2D system, it has to go through lot of resistant paths. While if you look at the 3D system, the 3D layers act like the vertically standing layers act like a highway for electrons, and electrons can go through very fast, and that improves the performance of the device, which Professor Fisher will be discussing later about when he talks about metrics and performance of devices. So when we go from 0D material to 1D material to 2D to 3D, what are the changes we are looking at? When we have 0D material or 1D material, we have, like for example, carbon dust or activated carbon. How do we put that material together? So we use some fillers, we use some binders, and then try to integrate it into an electrode. So what we are essentially doing is adding some resistant paths to bring the material together, right? So however, when we have 2D graphene or a 3D graphene, we have integrated individual layers which reduces the resistance between the electrodes. So you have increased conductivity when you go from 1D to 3D, as well as increase in the surface area. Here the surface area that I am talking of is the electrochemical surface area, which is accessible to the ions. It is not the surface area of the individual particles. If you take activated carbon in without any binders, probably you will see that it will have much higher surface area than a 3D system. But here I am talking of the electrochemical surface area, which is accessible to the ions. So this is throwing more light on the synergy between electrode material and the current collector. The conventional methods what people have used in the past, they involve slurry preparation with the activated carbon or carbon based powders, and then using some binders like Nephyon or many other things like some conducting polymers are as well used. While emerging and more novel technique include surface functionalization, where you bring the material on a template which can be in the form of a 3D architecture, or you can do some growth process. You can have a insulating template, and then you grow the material. These kind of methods have been discussed in the previous lectures, so I will not go into the detail. But these are more emerging methods which are used for these kind of device fabrication, because you need high surface area. Keeping that in mind, these methods are used. So from synthesis to processing of material, what are the different techniques which one needs to adopt? You have solution, you have particles in the form of a solution. Now you want to prepare a film, right? So it can be done either by, there are different techniques like spray coating or solution dip coating or rod coating or slot die coatings. There are a number of techniques like this. So these are the commonly used methods for putting the material together when you have it in the form of a powder or solution, right? But now if you want to grow 3D structures, you can use techniques like electrospinning. You can cast the fibers and then make it into the form of these wires, and they can be curled up, they can be molded into different dimension to make it into 3-dimensional structures. This is one of the approach. Second is electrodeposition, where you can take the solution in its precursor form, okay, and then you can apply electrical potential to grow the material. So these are a kind of summary of different processing methods that have been adopted in literature. A simple method could be taking the individual material in the form of solution and then filtering it to form a film. So here the film formation is very important when you go from individual particles or individual material and putting them into assembly. So like you have conducting material, oxides or polymers. How do you put it on top of carbon based material like graphene or CNTs? So their interface between the two materials also becomes one of the very important parameter. The stability, the adhesion. So these are the kind of things one needs to engineer when you are trying to fabricate any device. So here I have taken an example. Okay, you have particles, individual particles. Okay, their interconnectivity will decide how conducting they will be, right? So the connectivity, if it is through the particles here, as you can see, you will have some resistance, suppose R. Now, if I change or introduce some filler material into this system, particle B, if it is of the same size, then the electrical connectivity will be ensured. However, the resistance can increase if our resistance of particle B is different than our resistance of particle A. You can have increase in resistance of the system, right? And now if I introduce another particles which are slightly smaller than the particle A system, like particle B is smaller than particle A. In that case, the resistance of B can be much more than resistance A, and the overall electrode resistance will increase. So one needs to look at how the material is integrated together for making an electrode. Why it is important? If you look at the supercapacitor electrode architecture, okay, so this is one of the electrode, and imagine that these are the pores of the electrode. Okay, so across each pore has capacitors, because individual ions on the surface of the electrode is nothing but a pair of positive and negative charge. So that individually acts like a capacitor, and then there are multiple resistances across in each pore. So this can be represented by a simple diagram where individual pore itself is acting like a capacitor. So when you want to calculate theoretically what is the capacitance of a electrode, it is nothing but summed over different pores. So you can actually calculate over one pore and then add it up to have the total resistance or total capacitance. So for fabrication, different types of current collector is used to decrease the resistance of these electrodes. The synergy between electrode material and the current collector is very important, as I have been trying to highlight this point. So different conducting materials like metal sheet, metal mesh, metal foam, carbon foam, all conducting materials are used for making these kind of architectures. So for example, if you have a kitchen sponge, it is also porous, right? But it is insulating. One cannot use it directly as a support material for making a device. So you need a conducting backbone. So there is a lot of research efforts that are going on in converting these kind of insulating materials into conducting one. For example, nickel sponge is one of the material which is used as a current collector in many devices to support electrode material, because it provides a very conducting pathway for electrons or ions, or for electron collection on the electrode layer. Here is another example. It can be in the form of a metal wire itself. A core of the wire itself can act like a current collector. So one can grow material on the surface of the copper wire and then realize a electrode. You can see what kind of steps are taken to assemble a electrode itself. So you have first copper wire, then copper oxide is grown on it, and then again metal layer is deposited, and then again growth process. So you see here the growth process like electrodeposition or electrical coating is adopted to make hierarchical structures, which is important to get more surface area and for increasing the device performance. Now coming to the electrolyte side. The choice of electrolyte depends on its electrochemical voltage window, chemical stability, thermal stability, as well as the ionic conductivity. Electrolytes are characterized as organic, aqueous and ionic liquid. Now how do I decide, like with a given electrolyte system, the electrode will be positive or negative? So for that one needs to look into the electrode potential, okay, and so this is an example. Here this CV curve is corresponding to nickel oxide based system. So you can see in the whole range that you have current across the positive range. So this is used as a positive electrode for the system. How do we know what is the optimum concentration of electrolyte to be chosen? 1 molar, 0.1 molar or 3 molar, 6 molar? What concentration of electrolyte should I use for making the device? So it depends on the number of ions. But is it like one can use highly concentrated solution to get more capacitance or more to store more charges? There is a limit to that. So